All right, let's start. I will move some stuff. Right. The focus of this tutorial is to not per se take a deep dive into all the individual components of the social interaction cloud, but it's good to know they exist. But rather how to build your first application. Many of you have installed 6 successfully, and I guess also run some kind of applications, perhaps the Hello World application in the examples repository. But let's take a more in-depth look at how to build your applications and how to deal with a number of stuff. So after this tutorial, hopefully you know what the main components are of the social interaction cloud, but more importantly, know how to build your first application using the concept of syncing or locking an interaction thread and callbacks, using callbacks. And also, I want you to think about how you will be applying the application in an interaction context, in a human-robot interaction context. So one way to structure your interaction design is to first create a flow diagram and then create an implementation. And using a state machine or a finite state machine is a useful way to implement your flow diagram. So we'll cover that as well during this tutorial. So first, a bit about the basic architecture of the social interaction cloud. It's we want to control robots and perhaps other devices, but in this context, robots. But the processing power on the robot itself, there is a computer in there, in its head, but it's not very powerful. So if you want to do kind of computer vision tasks or even speech recognition, it's not very powerful to do that, only basic stuff, but we want to do more than that. So we need some solution to deal with it, to outsource our computing power. And that's where the cloud comes in. Well, currently you are all running the cloud locally on your machine. And that's where Docker is for, to basically simulate a cloud infrastructure. And the advantage of Docker is that we could run this same image with the same software somewhere in a cloud node or in parallel in multiple cloud nodes. But currently, we're not that far yet. So now you still have to run it locally on your machine. And we use Redis, which is essentially an in-memory database system, but it also has a very fast publish-subscribe type messaging system. So that helps us communicate between the robot and the cloud and other components, namely, for example, all kinds of services. So, for example, speech recognition is something, a lot of external commercial and non-commercial services offer these functionalities. So, why develop it from scratch ourselves if we can use very good solutions that are out there? So we want to connect to these kinds of services as well. You can also create your own services, but more on that in the lecture on next Wednesday. With Redis, we can, we can stream the camera, audio from the microphone, from the robot to our Docker instance where our Redis service is running, and then send that data in the form of specific requests, for example, speech recognition requests to Dialogflow. But this doesn't make anything happen yet. We need another component, and there are applications. I don't have a visual now, I guess, for applications. I missed that. But anyway, we're gonna use the Python API that exists to build applications, and application is in application layer. You will basically create all the logic for what the robot should do given input and given the goals you have with your application. Important to know, and that's what the next part of this tutorial will be about, is that this the communication is inherently asynchronous, meaning that if I would send an action to the robot, for example, wave, like it's doing on the picture, it takes time for this wave to be executed and completed. But your application doesn't know that. It doesn't know how long this wave animation takes. So it doesn't know how long to wait. So it will just continue. And for example, if you want the robot to wave, and then after it's done waving, start a conversation, if your application doesn't know the wave is done, it will start talking and starting to add more gestures, for example, and then you will basically lose control over the interaction because things happen not in the order you want to. So we need to deal with that. So that's what the first part will be about, dealing with asynchronicity. And the second part will be thinking in interaction flows. And instead of going over it in slides, I will do it in a form of a live coding session so that you can also see how it exactly works in the code. So I will stop my presentation. And so I have I have a PyCharm IDE for Python, and I will just create a new project. Let's do it in another location. And if you have any questions, please unmute yourself and just ask questions, especially if things are not visible or something, please let me know. I will zoom in on the code in a minute, but what I want to stress here is the importance of creating an environment in Python, because then you can install all kinds of packages that are accessible directly by your code. And this is all default in PyCharm, but similar things happen in other IDEs as well. So I'm just creating a new project, and I will want it a new window, and I will move this one back. Set that one here. So we're gonna just create a new Python file. My first application. I guess I can zoom in. Yeah, so hopefully it's better readable. Is it clearly visible, or is the dark mode confusing, or is it visible for everyone?
Yes.
Yeah, awesome. All right. So we have this project set up. We have our empty Python file, but to do something with the social interaction cloud, we first need to install the social interaction cloud Python package, and we can do that from the terminal, for example, from here. And be sure you have Python 3 installed and stuff like that, so you can check it. Okay, I have version Python 3.10 installed. There is a new 3.11, which is even faster, I heard, but I think everything from 3.8-ish would work fine, I think. So it's just pip install social interaction cloud. So now the social interaction cloud Python API is installed. I can actually import it, and what I'm going to need from it is the basic SIG connector. So I will just import that one. And what I like to do typically, but that's, I guess, part of my training. It's not obligatory to do it exactly like this, but you can see it in the examples as well. I usually create a class, for example, I'll call it my first application. I want an instance of the basic SIG connector to build my application. So I will create one in the init of this class, similar how I do it in the examples. And what this needs actually is, well, you can see all kinds of different attributes that it might need, but for a simple application, we just need the server IP. So that's something that this class will also ask when we create an instance of this specific class. And this is the IP of the instance of the place where you run the social interaction cloud. Well, if it's in the cloud, there is an actual IP, but now because you're running it on your machine, the IP address is just localhost, or the IP address equivalent of it. Let me see. And then we're gonna create, I don't know, some run method where the code will actually run. I will pass it for now. And then create a main. I did that, by the way, if you want some hotkeys for PyCharm. It's Control-J on Windows opens up this, I think, all kinds of code templates, and I just entered the main, Control-J main, and then I can enter it and I get this. Quick and easy. So I will create a new instance of my first application. And I enter the IP address, which I think could just be the word localhost. I typically use, but it's whatever works best. I think just the IP address of the localhost. And then I want my first application to run. well, it doesn't do anything right now, but it would set up the social interaction cloud, which I didn't start yet. So that is something I should do before starting. So I will start my Docker in the meanwhile. And then in the meanwhile, I can explain some basic concepts. If we go to the SIG connectors and dot, you get to see a lot of different actions you can start. For example, play motion is an action to make the robot do a certain motion, play audio, the robot to play some audio, say the robot to say something. There are also other aspects that doesn't directly send actions to the robot, but for example, you can subscribe event listeners or unsubscribe event listeners. So that's basically if events come in either from the robot or from a service, you can do something with the data coming in. So there is if we go to the wiki, I'm now in the Python connector page where the basic instructions are. There is some documentation where these actions are explained and what input they expect. Currently, I don't think it's entirely complete, so that's something we will work on in the coming week as well. But you can always use the Python doc basically. For example, do gesture. If I hit Control Q, it will fetch the documentation, and then you see basically everything that you need to run this action. So that's another way to see what other options are basically. Let me see if Docker has started. So now I will actually do the action. So I will just let you watch with me. I'm not sure if I can zoom. I can also zoom in this. Excellent. So I have to go to the folder where I have it. For this simple application, I just need Redis to run. So I just do Docker compose of Redis. And then it will start Redis and zoom out again. Not sure if that will work with this work. Yeah, well, smart. I actually have a robot here with me. I'm not sure if you can see my camera because I'm sharing my screen, but I will also put that up and just use the robot. Now on to the topic that I wanted to discuss, and that's dealing with asynchronicity. And the way to do that is every application basically starts by starting an interaction thread. So if you hit the start command, an interaction thread will start, and usually every application stops with the stop command. It will stop the thread and will basically terminate the program. And every action that you can take, I think, every action you can take by using the basic SIG connector, you have the option to either call it in a synchronized way or in an asynchronized way. So in an asynchronized way, it's just the way I explained. You send an action and you don't wait for it to finish, because the robot has no way, the application has no way of knowing when an action is finished. But we added some logic to it. Nordi asks, is there a time frame involved in the run function? Can you explain that question, perhaps? What do you mean with time frame? So there is no concept of so basically, like with all aspects, okay, so there is no, you don't have to do something with time explicitly. It will just run the program from start top to bottom, basically. And I will explain in a minute. Hopefully it will get that clear more in a minute. So, for example, if I want to say something, well, you have to get a certain text. I'm just saying what I'm, it's hello world. And there is an additional argument that you can give, and it is sync. And default, it is set to true. And this makes this action actually a synced action, which means that so a step back, there is a way for your application to know when the robot is done talking, namely through the events it's sending back. And one of the events, for example, for a say action is text done. So, or I am done talking. And the basic SIG connector has some event handling that you can turn on, and which is turned on by default, to make it wait until this specific event has been returned. So by setting sync to true, which is default, so if I don't have to type it here, it will actually block this interaction thread we just started before it continues. So actually the robot will wait, or your application will wait until the robot is done talking and saying hello world. So this is now done by default. There are certain cases where you don't want this to happen, where you want the robot to, your application to continue and not wait for a certain event to come in. For example, this is out of the scope of this tutorial. For example, for a vision service, where you want to have some information about how many people are in a screen, or if certain people, if faces are recognized or whatever, you don't want to block the whole interaction while the robot is looking and trying to detect faces, for example. You want to do this in the background. So if you want to do that, if you want to run something in the background, you have to put sync to false, because this is turned on by default to true, because in most cases you actually want to block the interaction thread, because you need the information whether the action actually completed successfully before moving on. Another question. And is it possible to set up callbacks? Yes, I will come to that in a minute. So that's basically the second way to do it. And usually you use them both at the same time. And yeah, let's just look at an example that I created. That's the synchronicity Python example. And I will just briefly recreate it here. So one of the things important if you want a robot to talk is to make it talk in a specific language. So that's where the set language comes in. And if you want to make it talk English, or we typically use the US English. So you need to use this language code to make the robot talk in English. Typically what we do is we put the robot in a crouching position on the floor, and to make it stand up, which makes interaction more fun if the robot is actually able to move, we have to wake it up. That's where this command comes in. And so I want to do something with body postures, and to make the robot sit down and stand up again and stuff like that. But to illustrate it, I'm now copying some stuff from the example, so you can find that there as well. So like I said, sync is on default, so it will say the sentence and then it will wait until it's done before continuing. And if we would add this sync is false to it, then it will not wait until this sentence is completed until moving on to the next action, which is to make the robot sit down. So there is actually, you can see here that it requires an enumeration, specifically the robot posture enumeration. And I don't think it's imported yet, but you can, in PyCharm at least, you can use Alt-Enter. I'm not sure what the Mac equivalent would be, but you can import the robot posture. And you actually see it's now added here. And we want the robot to sit down. Let's just see if this works. I will have to connect the robot first. That's something I didn't do yet, so I will do that now. So in the Docker repository in SIG local, you find all kinds of connectors. For example, you can also, if you don't have a robot at home, which I do, but you don't, I guess, and you want to test it out, you can also use the computer robot, for example, which simulates a robot. Basically, it takes actions and returns the event it would return when this action would complete. So you code, even though you don't have a robot, you can still run robot actions and make it continue. You need a computer speaker if you want the robot to talk, or if you want to have this, and you need a microphone if you want to say something to the robot. So I will, but I have a robot on here, then I need the robot installer. So I will just run the robot installer. I will get this screen. You don't have to change anything here, just hit OK. And then you get the connector. And the default path is now, and then you can just hit OK, and it will connect with, of course, the IP address of this of the now. But I guess you figured out that you can press the chest button once to acquire the IP address of the robot. So now everything is connected and installed on the robot. I can actually run this application, and if everything goes correctly, the robot should say this. And if it's done, move on to this. But while saying this, the robot should go to a sitting position. Because I want the robot back up, I will then also add this to make it stand again, because it's easier to run this program multiple times. Interesting. I get an error. Let me see if this example would run. Yes. That's strange. It always happens, of course, during the moments it shouldn't. I don't know what error I made, but to just move this tutorial forward, I will just move to the example in the, I think it's easier. I basically have the same code here. I will zoom in. And I will run this instead. I will just comment out the other stuff. To have exactly the same thing we had. I know exactly what went wrong. I think. So I will move back. I now notice what I missed, and that's something maybe you will also encounter if you encounter this error. What we forgot is that the application needs to, because we're using with communicating over SSL for a secure connection, we need a certificate to confirm we are a legit application. So in the examples repository, you will find a file called cert.pem, and I will paste it here at root level. It looks like this. This is basically our certificate saying we're a legit application, and I forgot to add it here. So a resolution at last. And there was a question, in which directory with relation to Docker does this my first app have to be in? It cannot be anywhere on the computer. And the answer is yes. because Docker will create a virtual machine inside and install actually, I think, Linux distribution is run in there, and there the social interaction cloud actually runs in. So it actually simulates being an actual server somewhere. So you can install this anywhere on your computer. Even you could run the social interaction cloud on a different computer, as long if you can connect to that computer. So if you have like a, I don't know, a heavy desktop at home and you want to do heavy stuff, you can in theory run the social interaction cloud there. And if you open the right ports and expose it through the right with an IP address, you can from anywhere basically using that IP address connect to the social interaction cloud from anywhere. So yes, you can just put this anywhere. So let's try this again, and hopefully now it will run. Yes, it solved our problem. That's also the advantage, of course, of doing these live coding sessions, is to, I want to move this. Yes, okay. Is that sometimes errors do occur, and then solving it will hopefully also solve if you encounter similar issues for you. You get this pop-up if you use the robot, at least. If you use only the speaker, my computer speaker, then I think only this one will pop up. And if you also use a simulated robot, which you need for this example to work, because it will sense actions specifically for the robot, like going to a posture, you need the robot and speaker. You will only see these two pop up, but you select them and then run them. And now what you can't see, what I can see is the robot standing up. Yeah. Maybe next time I can install like a second camera with the robot view. But the robot is, maybe you can hear the motors in the background. The robot is exactly doing what we wanted to do. And then in the end, you see that the program is terminated gracefully in the console. You can see, okay, then I can maybe point the camera also to the robot when it does something. All right, so that's basically how you can do synchronization stuff by blocking or not blocking the interaction thread. There is another example, or part of this example, that I want to go over, and that's about subscribing to events and making your program wait to it. So I will comment this out and just focus on a specific thing. So I covered like say, so like set language, wake up, say, go to posture, all actions related to the robot directly, say sending actions. But there is another aspect to it, and that is listening to events. And an interesting type of events are touch events. So the robot has all kinds of buttons, and if you want to have some kind of physical interaction going on, you need to listen at some points to if a user presses a button. So what I now want to do is to make the robot, or make your application wait until a specific button is pressed. So I will communicate this to the user by just making a statement, press one of my feet bumpers, which are the black bars, the toes of the robot, to continue. Next, I want to subscribe to an event of these bumpers. So we can subscribe an event listener, and also in the documentation for the robot now key, you can just Google now touch buttons or whatever to find the documentation for the robot, which events it will generate for certain specific buttons. But you can also consult the Python connector API overview and then go to events. And there are on event a whole list of different types of buttons and presses, and things are listed here as well that come in through the social interaction cloud. So you can also look here for which events might be interesting for you to listen to. There's a question by Simon, what does wake up do exactly? That's a good question. So the robot basically has two modes. One where when turned on, and of course you have also the robot being turned off. But when turned on, there are basically two modes. One is the passive mode and one is the active mode. And in the passive mode, the robot's motors are turned off, so you can move it freely, you can position it in any way you want. And the active mode, the motors are on. And it needs this, for example, for standing up, the motors need to be on, otherwise it will slump over. And you can't move the arms, for example, when it's in active mode, and it needs to be in active mode in order to move. So if you say go to posture, but it's still in passive mode, then it wouldn't do this action. So it needs to be in active mode to be able to move. And the wake up action changes the mode to the active, from the passive mode to the active mode, and the rest commands, which I didn't add here, but I think it's good practice to always end your program unless your context doesn't require it. But typically for testing as well, you want to end also with rest, so it will go from the active mode to the passive mode, and if it's standing, it will actually go to a safe crouch position for the robot not to fall over. Why is this important? Because maybe you will notice, or you've already noticed when using this robot the past week, is that its motors are prone to overheating. And that can, well, it will turn off sometimes, these motors, when it does so, and then you have to wait before it's cooled down until you can use it again. But on the long run, this actually damages the robot. So it's good practice to always, if you're just programming and not, if you're testing the robot, but there is a bug, I need to debug it, and you will take, 20 minutes to do this, and the robot is standing there with its motors on, it will overheat and damage the robot. So please, in these moments, put the robot to the resting position. What happens if you have a bug in your code and it doesn't reach this rest command? It will actually just stay upright in active mode. So what you can do is, I'll try to show to the camera, you can press the chest buttons rapidly twice.
Error 600.
Oh, yeah, that's because I'm carrying it. It will actually go through the rest mode, which is now, I messed this up because I moved it in the air. But if you press it twice, it will usually turn on what's called autonomous live, which is some standard out-of-the-box behavior of the robot where it simulates awareness and looks around and stuff like that. And if you press it twice again, it will actually go to the rest mode. So that's a way for the robot to, for you to turn the robot into the passive mode when your program crashes at some point too early. Excellent. Moving back to the event listeners. So what we want to do is the robot to wait until this event comes in. A user presses a button, before the program continues. So I'm just copying this from the example, but you can look at it up at the different sources I just introduced. So this is the event coming in when the right bumper is pressed. I can just copy this and change this to left. That's when the left bumper is pressed. But what we now actually can do is what happens now is that the robot at this point will wait until the right bumper is pressed. That's not what we want to happen. We want to let the robot wait until one of these is pressed. So what we actually can do is preload them, but not run them immediately. So we can use the load attribute, load argument, and set this to true. It's default false, so it doesn't load by default, but you can set this to true. So which means I'm not running this right now. I'm just loading it in and waiting for this method to be called the run loaded actions. By default, run loaded actions will run all the previously loaded actions and will clear all the loaded actions after it's done. So if you would load new actions here after this command, these actions are not part of that list anymore. So it will just run all the loaded actions up until that point, and will clear the list. And by default, it will wait until all of these loaded actions have been completed. Or in this case, it needs to have this event come in for both. So if we actually would run this, we have to press both feet, both the bumpers of the feet to make the program continue. If I would, for example, in this case, it's not makes sense, but just for you to know, if you would call sync is false, it actually won't wait for these. So it will only wait for the actions where sync is set to true, which is by default. So you can exclude if you have a longer list of actions and event listeners. But for actions, you might sometimes want the robot or your program not to wait for it to finish. So you can set this one to false, and this one is actually excluded from the waiting. But now we want this robot to wait, your program to wait. So we don't want to set it to true. But there is an alternative. We can basically choose if we want your program to wait for all or for any. So that means if one of the bumpers is pressed, then we want your program to continue. And that is done with wait for any set to true. So its default is false, meaning it will wait for all. But by setting it to true, it will wait for one of these loaded actions to complete. And in this case, it's an event listener, so it means that this event has come in. We'll just make the robot say something here as well. Let me see. Yeah, so if we would run this program now, then it will wait until I press one of the buttons of the robot. Maybe I can turn my camera to the robot. That would work. I will first have to start the program. Now I can't see it. So I again get this pop-up screen, and then I will just and then run.
Press one of my three bumpers, my toes, to continue.
So now it will wait until I press a button. Let's just press a button.
And done.
Now it's done. And to illustrate the point, if I would remove this, we'll just see what happens then as well.
Press one of my three bumpers, my toes, to continue.
So now I'm pressing one button, it doesn't continue.
And done.
And now I'm pressing the other one as well. So I have pressed both, then it will continue. Let's move on to the callbacks. Let me open up that example here so I can look at the cheat sheet. Yeah. I think I will just remove this and use this as the base. So typically this is what you want to do for most of your programs, to set the language to English, wake them up, and at the end, rest and stop. So the question, does the subscribe event listener basically mean that the robot is expecting an input from the user? Well, not necessarily the robot, but your program, you as a programmer are expecting an input. You can deal with this differently. So for example, if you want, if it's an optional input, for example, so your program can continue. So this is specifically, okay, I need to have a certain input. So for example, the user needs to make a decision, go left or right, and you need this information for your interaction to continue. You want your program to wait before this information comes in, and they can press the right or left bumper, for example, for the robot to go right or left or whatever. But there, of course, are also cases where you want you just have a conversation, and whenever the user presses a button, then the robot does something, but it's not something that needs to happen exactly at that moment, or it needs to happen at all. It can be truly optional. Then you can subscribe an event listener and set sync to false. Then it will have subscribed to this event, but your program doesn't wait on the event to actually come in. So how I demonstrated it in this example, it will wait, but I think maybe we can also make an example where it doesn't have to wait. But to actually do something at that moment, we will need callbacks. So that's a nice bridge for the next segment, and that is callbacks. So in the example, I used audio recording because I like that feature, but unfortunately in the current implementation of our SIG framework, audio is directly connected to using Dialogflow. So for now, so this is something we want to disentangle in a future update, but for now, audio recording and Dialogflow are tightly connected. So in order for us to actually record audio, we need to set up a connection to Dialogflow. How to do this, I will explain in the lecture next Wednesday. But for now, I will just add the stuff we need. and that's three things. We need to add the dialog flow language, the key file, and the agent ID, which will pass through on this level. There is on the wiki, there is also explanation on how to set up a dialog flow agent, which you will need anyway for speech recognition. So now we need to add that here. So to connect to dialog flow, you need a key file, which is something you can get from the dialog flow interface. So I have a simple dialog flow agent here. There are already intents that I created here, which are part of the speech recognition example number 3 in the examples repository. And you can actually find these intents in the resources folder in the example repository. So you can upload that in your own agent as well. But for now, we don't need any intents or these things. We just need a connection to dialog flow in order for this for us to record audio. So I will just copy the key file that I downloaded from the dialog flow webpage. Instructions are also listed in the wiki, the Confluence wiki. And I will also go over it in the lecture, but for now we just need to have this file, and we need to add these 3 things here. So we need the language key, which is just the same as, the robot listens to English as well, not only speaks English. Then we need to have the reference to the key file, which is just, in this case, it's in the root, so we can just directly reference it. And we need to add the agent ID, and which is basically just the project ID here. So I can just copy this and paste it here. So now our application is able to record audio. Because I want to use the audio file coming in and to use that as an example for dealing using a callback function. So in my research, I work mainly with children, and making sound effects for the robot is something children like to do. So I always love to see this happen in practice. So we want, in this case, me, roaring like a lion. So the robot will count down, and then it will, I want to make it record audio. And what we need to add here is a duration. So that's the only required element. So just, 3 seconds is enough. But in order to get the actual audio file, or the link to the path to the audio file, we need to use a callback. And that's something we can add here. And a callback is a callback function. So we need to define a separate function that will be called, will be triggered on the moment the robot actually recorded the audio, and there is an audio file saved on your machine, which will be saved here in root, we will see in a minute. So what we need to do is, let me see, just create a callback function. So we can just, in this class, we can create a new function saying, for example, I don't know, typically event listeners or callback functions have this structure on, and then something that it gets, so on audio file, and we will want to we get a file name. That's what we get in return. So also what the callback gets back is also something, and if it's not completely there, we will update this also the coming period in the wiki page on the where all the actions are listed. So we actually get well, it's maybe not a file name but file path, but no, maybe just anyway, it will be en route, so it will in this case be the same. So what we want to do is to store this. So we will add different class variable here. I don't know, lions roar, which is empty in the beginning, but hopefully we will get that back here. And let's just, I don't know, for now, print this in our console. Maybe we can, to demonstrate when we actually able to access it, is in a moment. So at this point, we should be able to have this value filled. So we actually know if there will be input or not. So now we can actually add this method that we just created, this function as a callback function here on audio file. And very important is to enter it without these brackets, because that will actually execute this function rather than just pass along the reference to the function. So this will pass along the function without actually calling it at this moment. It will be called when the audio file is actually there. So one thing we need to do before this program can be run is that currently we only run Redis, but we need to have the Dialogflow service running as well for audio to be recorded. So what I will do is I will disconnect the robot, because we will actually have to stop the whole Docker instance, not Docker itself, but the Docker container. So we will, I did just Control-C to terminate it, and now I do Docker. I will zoom it in, we'll compose down to really make sure everything is closed. And then instead of Docker compose up, I will use Docker Dialogflow. And actually Redis is started by default whenever you run any service. So in this case, I'm running Dialogflow as a service. It will also start Redis. And now this is all created. I need to reconnect this because you see an error here because it lost connection, because I actually closed down the Docker container. So I have to rerun this and reconnect to the robot. This is again the IP address currently for the robot. And now and enter. You see. So now everything is up and running again. Dialogflow is running here. I can run this. and see what happens. I get this. And for this example to run without the robot, you will need a microphone, computer microphone running instead. So the robot is standing up.
Roar like a lion in 3, 2, 1.
Roar, roar. So now actually there is a new file that's here with the audio of what I've just did. And the fun thing now we can do, this is just something extra, is that you can actually make the robot play it again. So we actually have this file here. I can play audio and then add the lion's roar here, and it will actually play the file back what I just recorded. So you can have a little fun with this yourself as well. Given the time, we'll just move on to the next segment, and that is interaction flows and state machines. So I think most of you have created flow diagrams before, so that's a good way to start thinking about your interactions and designing them. So for example, what I use sometimes is draw.io. It's linked to your Google Drive, and you can create a flow chart. To authorize all these things now. Oh, okay. Not sure why I can't connect. Oh, okay. This also works apparently. And you just can use these flowchart things, for example, decision making and stuff, and to really build these these interactions in this way. And it helps, so I won't do it now. I think there are also other courses more dedicated to this part, but just know that this is a way you can think about your interactions. So what's important here is that you start thinking in trying to make your interaction more modular. So one way to make your interaction more modular is, of course, to create different methods in your code for different functionalities. I will just quickly show it in the example of speech recognition. So one way, so this is a pretty hefty example with a lot of code. I will go over it during the lecture on Wednesday. But what I did here is a lot of documentation as well, is to, instead of for every question have the logic for question handling copy pasted, I don't know, if you have 10 questions 10 times in a row, of course, you know, this is bad programming. So these are just basic programming stuff to structure your code. But given the experience with the last 3 years, we felt that we really need to stress this more, because often students resorted to just copy pasting the code after each other. So just create different methods for different functionalities. For this example, for example, here, ask a yes or no question, and the handling is done here. So you can imagine that if you would copy paste this code every time you ask a question, that you get a very long, unreadable code. So please, you know, if you want to ask another question after this question, I can simply say ask yes, no question, and, you know, question. And the code is so much cleaner that way. But this example, what this example still does is go through an interaction linearly. So from you assume there is a beginning and there's an end, and there are a fixed route through this interaction. For simple interactions, this is the case. For some more complex interactions, you can also get away with this. For example, I don't know, a storytelling example, which I use often with children. You know, the robot just follows the story. Although it's a longer interaction, it still has this linear route. But often, it's not as linear as you might think, or there are all kinds of, you know, you have the happy path, which is linear, but there are all kinds of ways things can go wrong or deviate. Especially if you want to give more control to the user, there are more options you need to consider. And thinking in a state, using a state mindset where you define different states and move from one state to another and possibly back again, you have more flexibility to create this non-linear interaction, but still create your code maintainable. So that's where the state machine example comes in. It actually uses speech recognition. That's why it comes after speech recognition. But for now, we can skip over the contents of each of the methods, but rather talk about the states themselves. So this example, we actually use a special package called transitions, which is one way to define state machines. It's a state machine library for Python. That's what it is. You can find more information about this and also about this example in the documentation. So please read about it. It's if I'm going back to the Python main page, there is Python connector background information. And on this page, hopefully we will able to fill this more, but currently it's focused now on the state machine. And there are references here to blog articles. So this is just background information about what finite state machines are and how they work and how to think in terms of finite state machines. And also a link to the library PyTransitions, what I referred to, with I think also this is the transitions we use, with a lot of information about how to use it. So this example you can use to really understand how this library works, and you can, I think there is even I see now a GUI, a front end, so you can actually draw your interaction in this flow diagram and then compile the code from it. I think what's happening. So please look at these resources when you're starting designing more complicated and bigger programs. So I don't have time to go into detail now, but I will just show this example that's in the examples library and go over it really quickly. So first of all, there are states. So the robot is either asleep, awake, it's introduced. So so these are, look at the language, asked, name. So these things have happened. So there's a state where some conditions are true. So in this case, the robot and the user got acquainted. And how to exactly set this up is also explained in the documentation of this PyTransitions package. But you can create a machine and start with an initial state. So it starts asleep, and we basically here have the state machine example where we just start the basic SIG connector. We start SIG and example robot is the state machine now. So maybe that's not the best wording, but this is the state machine where we also pass SIG as an input so that it actually can run. And you start the state machine also by the start command. So this is a bit confusing that you have to start it twice. So this is starting the interaction thread of the SIG infrastructure, and this is starting the state machine itself. But if you have, take your time into exploring this example also together with the documentation provided by the PyTransitions library of and the main component, how could it else be if it's called transitions, are the transitions. So transitions have a trigger, which means this is a method actually. So this is not a state, but a method that will trigger a state transition from the source state, meaning in this case asleep, and the destination state. And these are not actually methods themselves, only start in this case, but rather state transition labels. So they are more labels than actually what are methods is for example, wake up, because that's something we have here, and introduce is the trigger which is triggered after this. So you refer to using the after to the next trigger. So you have a trigger start, which actually you trigger by all the way down this, what I said, like you start a state machine, that is the first trigger, always the first trigger. So the first transition always starts with the trigger start. So it moves, it's a straight transition between the sleep state and the awake state. And before actually it can do this transition, it needs to execute this function, namely wake up. And this is something that makes the robot go from the asleep to the awake state. But you need to have the content of that transition is defined in one of the class methods. And it will trigger actually the next state transition. It doesn't have to, so this is an optional aspect. So this is basically still a pretty linear interaction, but then shaped like a state transition in a state transition model. So sometimes you don't have to trigger a next state transition in one state transition, because there are other external triggers that happen and force a state transition. But in this case, there are no other additional external state transition triggers. So you can also trigger state transitions within a previous state transition. So hopefully, maybe it's a bit confusing as I'm going over it pretty quickly, but the example in the documentation of in the GitHub page is pretty solid. So a lot of explanation here. So just go over this to really fully grasp what's going on, because we know from past course years that this is one of the things students have trouble with, is to really design elegant and robust code and resort to, what I said, like copy pasting these long if then else statements, which is not very maintainable. So please check this out and take your time to explore this, to really think in terms of states and state transitions. So just finish up this example. This state transition, the first one triggers the next one. and that is the introduce state transition. It will transition from the awake state to an introduced state. So before this can happen, before the robot and the user are introduced to each other, an introduction needs to happen, and that's exactly this method was for simple. I'm a social robot, and this goes on. So okay, then the next state transition that will be triggered is get name. That means from going from the introduced state to the asked name state, and you need to ask the name. So that's what happens here, and etc. So there is also we can use conditions. So now we actually have two different state transitions that have the same trigger, namely get acquainted, which is triggered here. And that's dependent on whether the speech recognition attempt actually succeeded. So in case it did, the has name, which is, I think, do we have, yeah, it's a Boolean function. So that's how you can create these conditions, is to create a Boolean function. And this basically checks, okay, is the name part of the user model, which is inserted in the user model if speech recognition is succeeded, and isn't inserted in the user model if it failed for some reason. So the condition is, okay, it has the name, this is true, then it will execute the function get acquainted with, which is here, and we have also one without. So this basically says, oh, nice to meet you with the name, or without, nice to meet you without the name. So in this way, the interaction never breaks, regardless of the outcome of the speech recognition attempt, but you can use the information, the name, if you have it. And so we have the conditions, and the other same state transition with the same trigger has unless has name. So this is basically a reverse condition, like a negative version of this condition. So this is a nice way to deal with, well, what I just showed here. And this is a decision node. With these types of decision nodes, you can define, two different outcomes or multiple outcomes, and use conditions or unless to define these different states. And then we have the rest state. So to show this example, so of course the source. So we now have basically two sources, namely get acquainted without and get acquainted with. But technically, you could also have even more. So we can use the star operator here to, okay, any state as long as the rest operator is triggered, which could, in some cases be useful. For any reason your program needs to stop, it will just call trigger rest, and it will go from any state to the asleep state. And it always has to say goodbye before making the state transition. So this is a very basic example of still a pretty linear interaction, but in a state transition shape. But of course, by not having an after trigger, for example, you can also trigger these things externally in your program. For example, by registering a vision listener, and as the robot is just, doing some stuff, going from state to state, and then it sees a new face, and it will transition to a different state where it will try to introduce itself to the new face it sees, for example. And this is not a linear interaction in that sense. So you can build that also pretty easy with the finite state machine approach. So that's it. I will, I think, stop share my screen. So are there any questions? A question earlier, you mentioned running computer robot jar to run simulation of the robot at home. Can you show how this works? Yeah, I can. I have to share my screen again, I guess. I will, for the example, disconnect with the robot, and I will start the computer robot. So I'm again in this SIG local folder of the Docker repository, and I can run a computer robot. I get this screen again. This is just connection to SIG. You can just remain this unchanged and press OK. Then you will get this basic screen, meaning that it's started. So if we would go to, for example, maybe the synchronicity example, let's just run this. Is it saying something? Yeah, it's also saying something. So I also need the speak functionality. So I will also start that. Oh, it's force of habit. So I get this screen. It's not playing audio now, so I'll open both. But I will think I will, if I just press this, I will. So I will start this, run synchronicity example. So now I only get the robot and the speaker because I didn't connect a camera or a microphone, which are not needed for this example. And I will select these, and then I will open. Yeah, so stuff goes a bit out of order here, but just to show what happened, all the robot actions it added here, and it actually used eSpeak to do the speaking actions. I'm not sure exactly. I think the events are returned immediately instead of after, going to a posture takes time. And because we have here these sync false things, stuff went a bit through each other. But basically you can now run this code without having to have the robot. That's basically what it does. The robot doesn't use eSpeak. The robot has his own speech synthesizer installed on the robot. So it's a different, it's independent of your computer. So that should work. Any other questions? You can type them out or unmute your microphone. All right, I don't think any questions are coming in. So I will stop this. So yeah, thank you very much for attending this tutorial. Hopefully it gave you some insight into how to build your first application, what the options are, where to look for more information into programming everything. And if you have any questions, you can always, of course, approach your TAs to help you out and to point you in the right direction when needed. So I will see you on Wednesday for the tutorial on speech recognition and gesturing. All right. See ya.
Thank you.
You're welcome.